All right, so everybody got their quiz back? My solutions are on the back side of the grade sheet as usual. This Thursday, we have a quiz. It'll cover vectors and probably a law of signs problem that we're going to talk about today. We might not finish the section on law of signs entirely today, but we'll get a good bit of the way through it. Enough to include on quiz. Get some practice. And then recitation today, it's a practice quiz, which I haven't printed out yet, but it'll be, I'll have hard copies there. Does anybody have any questions they'd like to ask? Okay. Then what we'll do is we'll finish up. We got through like the first section on vectors, and then we're just going to do a couple of application problems today. That won't take too long, and then we'll get started on a new chapter I've got a handout for you. We've done some vector application problems before last semester. So let's dive in. A ship's navigator determines that the ship is moving through the water at 28.2 kilometers per hour. So like, I guess that means if the water were still, right, like that's how fast the ship would be moving. With a heading of 26.3 degrees north of east. But the ship is actually moving at 31.1 kilometers per hour in the direction of 33.7 degrees north of east. And then we want to find the velocity of the current. So it looks like maybe the velocity of the current, or the current is like helping it move along, like maybe it's going with the current mostly. It makes it go a little faster, or maybe changes its heading a little bit. And that makes sense, like it makes intuitive sense that would be the case. And we should be able to figure out the velocity of the current from this information. So I think the idea, let's say VC is velocity of current. Vs will be the velocity of the ship through the water. And then VT is the total velocity. Like its actual velocity, maybe in reference to the land or the shore. And so the basic idea, I think, that's going to help us solve this problem is that the total velocity should be equal to the velocity of the current plus the velocity of the ship through the water. This would be true even if the current was working against it, right? It's just that if the current was working against it, these components might be negative or something, right? Like, so I think this is universally true. And then we'll just sort of see what, how we manipulate this equation. We want to find velocity of the current. So maybe what we could do is just manipulate this equation first. So if we subtract the velocity of the ship through the water from each side, we get that velocity of the current is the total velocity minus the velocity of the ship through the water. And the way we subtract vectors is just the same way that we add them component-wise. So we could find the components of these two, only now we're going to take the x component minus the x component and the y component minus the y component. The order matters now because we're subtracting. So let's find these components. They tell us that the ship is moving through the water at 28.2 kph. So let's use that information. At an angle of 26.3 degrees. North of east. North of east is really the standard position angle, right? So north of east would be as measured from the positive x-axis. So we don't need to make any adjustments. Both of those vectors, they give us the angle north, as measured from the positive x-axis. So we could find the x and y components. We'll do magnitude times cosine. And then magnitude times sine to get the y component. .3 for the x component, and then .5 for the y. The total velocity, they tell us, is 31.1 at an angle of 33.7 degrees. And do the same thing here. .9 for the x component, and 17.3 for the y component. How are we doing so far? Now that we have the components, we'll just do the subtraction, right? Sort of taking our cue from that relationship there. So the x component for the velocity of the current is the x component for the velocity, the total velocity, minus the x component of the velocity of the ship through the water. Similarly for the y component. So 25.9 minus 25.3, which is 0.6 for the x component. And then this is 17.3 minus 12.5, which is 4.8 for the y component. We have our components. What do we do now? Mm-hmm. Yeah, right. And this is a first quadrant vector, so we don't need to make any adjustments to that angle. So, let's see, 0.6 squared plus 4.8 squared, all under a radical. .84 approximately. and the angle arctan of 4.8 over the y component over the x, so 4.8 over 0.6. (82.9 degrees). So now we just got to put it together. 4.84. This is an application problem, so there's some context. We should include units. Kilometers per hour at an angle of 82.9 degrees. How's that? Is that going to help you wake up and be more lively? Bring enough to share for everybody, and then we'll all be like super excited. What's that?
It's going to be like 40 dollars.
Sweet. Good. You're good for it. Okay. So let's do another one. A lot of, there are some physics applications that involve forces acting on an object. So this one is kind of like that. There's a nice drawing of a Vermont Tech sign hanging on off the side of a building. Yeah, pretty good. So they tell us that the mass of that sign is 225 kilograms. It's supported by a cable, and we want to find the tension in the cable. So basically, I could think of this point as being like the origin, right? Like imagine there's some XY axes there. I've got that sign that's sort of pulling down, and then it's being held up, right? It's being held up by this cable, so there's a tension in that cable holding up the sign. In these types of problems where you have like something hanging on something else, or like, something being supported maybe by something else, the whole idea here and like what we're going to use to solve this is that sign isn't moving, right? It's just hanging there. Since the sign is just hanging there, that means that the tension, the y component in the tension, is just perfectly equaling out the y component pulling down on the sign. If they weren't completely equal, then the sign would either be moving downward, falling down, or being pulled up. But it's just hanging there. So those y components actually have to be perfectly equal to each other and opposite, right? Like just opposite directions. So if we, when I start a problem like this, I like to just draw it kind of on the axes. So I've got this sign, and that sign is all y component. It's 225 kilograms straight down. So I know the magnitude. What's the y component of that vector? Well, the vector that I just drew, this vector? What's the y component? It's negative 225, right? The components are signed, right? They're positive or negative. And the x component is 0. And then we have this tension vector. Going up this way at, we got 40 degrees. It has some components there, and it also has some magnitude, right? But what helps us solve this problem is that we know what the y component of that vector has to be, right? That has to be 225 straight up. Whoops, sorry. So the sine is exerting 225 kilograms down. And that means that the y component of the tension vector is positive 225. Awesome. They wanted us to find the tension in that vector, or the tension in the cable, the tension which is a vector quantity. We already essentially know the angle. I mean, it's 40 degrees from, as measured on this side. If I wanted to see it as, if I want to kind of keep the perspective of being on this side, I could easily say, well, that's going to be 140 degrees. That's fine. Of course, I could just get up and move to the other side of the sine and be seeing that 40 degrees as its standard position angle. But this is all about finding the magnitude. So if the y component is 225, that means that since the y component is magnitude times sine of theta, and I'll go ahead and just see this as 140 degrees. The y component's the same regardless. The y component is positive in both the first and second quadrants. So we get 225 is magnitude times sine of 140 degrees. And we can find the magnitude just by dividing both sides by sine of 140 degrees. $350 degrees, or sorry, that's not an angle, 350 kilograms. 350.04 kilograms. So here's our tension vector. 350 kilograms at an angle of 140 degrees. If you wanted to say it was 40 degrees, because obviously you could just get up and walk on the other side of the line, on the other side of the sine, that's fine. You get the same result as far as the magnitude or the finding that y component. Yeah, we don't mess around. Like it's granite or something. What?
It's like 480 pounds.
Yeah, it's big. It's big. Yeah. So you gotta have a good cable that can handle that kind of tension. What? Oh, okay. Yeah. Are there questions on how we set this up? So I mentioned, I said, it doesn't really matter if we think of it as 40 degrees or 140 degrees, right? You can just get up and walk on the other side of the sine, and the components are, y component's still positive. It matters. I mean, you can, in a scenario where, you can have that change of perspective. I think we did another problem with looking at a wagon and a handle on a wagon, and I drew it one way, but we could just sort of view it in the other direction. You can always do that in those situations. You do want to be a little bit careful because, if we were talking about x components here, we would just have to be aware that if I draw it this way, the x component is negative, and then I need to use that 140 degrees, and that'll still work out to give you the positive magnitude as we should get. And if I got up and kind of drew it this way, the x component is positive, and I need to use an acute angle. When you're working with the x component like that, it's possible to make a mistake if you change the angle but then don't adjust the signs of your component. That can mess you up. But you would be able to tell in a problem like this, because in that scenario, if you made that mistake, you'd get a negative magnitude, and magnitude is always a positive value. Questions before we talk about oblique triangles? Oh, Jacob. Don't Don't. What does that even mean? I'm glad you asked. We're going to learn about it. We're going to learn about it. An oblique triangle is simply not a right triangle. It's just a triangle that doesn't have a right angle. That's oblique. See, we're already learning. That wasn't so bad. They're super fun to solve. But, you know, here's one thing I'm going to say. I want everybody to stop what you're doing and just listen to this. This is super important. When you're solving or working with an oblique triangle, you have to remember, tell yourself this. You can't use Pythagoras. You can't use SOHCAHTOA. Those only apply if you have a right angle, right? Pythagoras holds for right triangles. SOHCAHTOA holds for right triangles. Throw both of those out the window, okay? We're going to kind of use right triangles to help us construct one of the rules, one of in today's rule, the law of sines. But just like the number of times I see people starting on solving an oblique triangle, and they'll do a bunch of good work, and then they'll try to apply Pythagoras. And I'm like, oh no, that's not going to work. So just be really aware of when rules apply, right? We get so used to being able to apply Pythagoras because it applies in a lot of situations. We're allowed to, we're able to kind of impose right triangles in a lot of scenarios, right? Kind of, we got a point in a plane, drop down a perpendicular, bam, you've got a right triangle, perfect. But we're going to be working with triangles that almost exclusively have no right angles. So there's, when we solve a triangle, it always means fill in all the missing information, meaning any sides we don't know, find them. Any angles we don't know, find them. So there's different scenarios. It's possible we might know two angles in one side. We might know two sides and the angle opposite one of those sides. We might know two sides and the included angle. That's different. And then we might just know all three sides. In all cases, we need three pieces of information, at least one of which has to be a side. Okay? That's because if I just know all three angles, there's actually infinitely many triangles you can have, right? Just blow it up or shrink it down. The angles will be the same, right? The sides will be in proportion, but that doesn't uniquely define a triangle. We have two rules that we're going to use, two concepts to solve these. And we're going to focus on the first two cases today. And in the first two cases, we can use the law of sines. To solve. The last two cases we'll do next week, or not next week, probably on Thursday. Well, we'll see when we get to it. The last two cases we'll use the law of cosines. By the way, this chapter is going to be the end of material that's going to appear on the first test. I will have... Did we talk about this last time? We'll probably finish this chapter maybe a week from today, possibly a week from Thursday. This section that we're starting now takes a little while to get through. I'm pretty sure we talked about this last time, but I'm still thinking the 20th roughly will be when we'll schedule that first test. I'll have a problem set ready to hand out either Thursday or a week from today. I'm going to aim for Thursday, but I don't want to make any promises right now. You'll have at least a week and a half to work on it, or at least 9 days. Okay. So let's talk about the law of sines. Here's how the law of sines works. We start with a triangle. And as usual, we're using these lowercase letters to label the sides. And then the uppercase letters, the capital letters, are the angles. And angle A is always opposite side A, angle B is opposite side B, angle C is opposite side C. We have that convention. What the law of sine says is if you take the ratio of the length of the side to sine of the opposite angle, like side A divided by sine of angle A, that ratio is constant no matter which pair you take. That's what this says. And we're going to derive this fact first, and we're going to do it by imposing a right triangle on this scenario. How do I make a right triangle here? What could I do? Drop a perpendicular. Brilliant idea, Jacob. Okay. Let's drop this perpendicular down from angle C. So then that length of that perpendicular is the height of the triangle. So I'm going to call that H. Now, since we have a right triangle, in fact, we have two right triangles. We have this right triangle here, and then we have this right triangle here that both share this side, H. So let's use, since we have a right triangle, let's use SOHCAHTOA. Let's use SOHCAHTOA on angle A. And in fact, we'll use the sine version of SOHCAHTOA. What is sine of A? H over B. Great. And now I'm going to just solve that, rearrange that to solve for H. So H is equal to B times sine of A. Let's do the same thing, only now with angle B. What's sine of B? What?
Also H over B.
Why H over A? I like that you said that, but why?
H is opposite.
Oh, H. You said H over A. Yeah. H over A. We get that from SOHCAHTOA. So H is A times sine B. What's an equation we can write? Like, take a look at these two equations. How do we make a new one?
B times sine A equals A.
Can you say that louder?
B times sine A equals A times sine B.
Yeah, they're both equal to H. The height is constant, right? They're both equal to the same thing. So these two have to be equal. So B times sine of A is equal to A times sine, whoops, little a times sine of B. And now we're just going to do a little algebra. I'm going to divide both sides by the same thing, and what I'm going to divide both sides by is sine of A times sine of B. On the left side, the sine of A cancels. On the right side, the sine of B cancels. And we get, on the left, B over sine B is equal to A over sine A. So there's part of the law of sines, right? If I wanted to make the equation that involves angle C, I could just draw a perpendicular from another angle, but that's the idea. So, huzzah. I'm going to declare victory right now. Okay. Let's do an example where we use the law of sines. There's a couple of things I want us to keep in mind as we go through. You know, we can't check with Pythagoras or SOHCAHTOA anymore with our oblique triangles, but the angles still always have to add up to 180. Also, biggest side is going to be opposite the biggest angle, shortest side is going to be opposite the shortest angle. And we should keep that in mind. That can help you detect errors. We begin with a case 2 scenario, two sides and the angle opposite one of them. So I've been given two sides, and then one of the angles I know is opposite one of the given sides, one of the known sides. Using law of sines is all about having a matched pair of like a side and its opposite angle. So since I know the side and the opposite angle, what we're going to do, first of all, there's one side we need to find. We're not going to use Pythagoras to find it because that won't work. And then there's two angles we need to find. So the first thing we're going to do is find an angle. And what we can do is use the fact that, let's see, we could find angle B first, because I have this matched pair, and then I have an incomplete pair here. I can't do anything with side C or angle C yet, because both of those are unknown, so like I just have to leave it. But I can find angle B. We have to be careful when using the law of sines to find an angle. We have to be careful, because what we're going to do first is find out what sine of B is equal to, right? And if I know what sine of B is equal to, then how do I get the angle B? Arc sine. And so what's true about arc sine is arc sine will give you an angle between negative 90 and 90. And if you're finding arc sine of a positive quantity, which we always will be here, okay? When you're finding arc sine of a positive quantity, it will only give you an acute angle. So we have to be careful, because if the angle that we're looking for could be obtuse, our arc sine function won't give it to us. But I know for sure that angle B is going to be less than 65 degrees. And why do I know that?
Because 65 is 20 is the side length.
Because what?
65 degrees is 20 is the side length.
Yeah. Yeah, right? Like those angle sides and the length sides are kind of corresponding to each other. So angle B has to be, this side, the side opposite angle B is shorter than the side opposite angle A. Angle B has to be smaller than angle A. So that means that when I use law of sines and I'm using the arc sine function to figure out what angle B is, I know that that acute angle that arc sine is guaranteed to give me is going to be the angle that I'm looking for. So we have A over sine of A is equal to B over sine B. Let's plug in what we know. 20 over sine of 65 degrees is equal to 15 over sine B. We can set the cross products equal here, because we just have a simple proportion. So we get 20 times sine B is equal to 15 times sine of 65. And then just divide by 20 on both sides. So sine B is equal to 15 times sine of 65 degrees over 20. Some people put that in the calculator and get an approximation for that first before they use the arc sine. I usually just leave it as is. You could do either, that's fine. If you compute it first and then do arc sine, just take it out several spaces. Don't round that value too coarsely. So angle B is going to be arc sine let's see what we get. Let's see. So arc sine 15 times sine 65. I'm closing out that sine parentheses, and then I'm dividing by 20, and now I'm closing out the arc sine parentheses. And I get 42.8 degrees. So there's one value. Now with here's one difference when we're solving oblique triangles versus right triangles, aside from the fact that we can't use Pythagoras or Sepultura. When we were solving right triangles, we could always find everything we were looking for by using only the given information. Now, when you're solving oblique triangles, you're really forced to use values that you found, that you calculated to finish solving. So, what's the next thing I'm able to find right now? Say that again?
Angle C.
Angle C, right? I know two angles. So angle C is I know all of these have to add up to 180. So note right now that I'm using the fact that the angles add up to 180 to solve for an angle, so I can't really use that as a check anymore, but I'm going to make sure that the side lengths sort of correspond with the angle measures. $72.2. Okay, so we found that angle B was less than angle A, which is what we expected because of the side lengths. We found angle C is 72.2 degrees. Before we go about solving for side C, what am I going to expect? What kind of value should I get? It's going to be more than 20. Side C has got to be the biggest, got to be the longest side. And that's sort of our check that we have. It's not a perfect check, but it's a kind of a quick kind of does this make sense check. And actually, I'm going to go down here to do that so I have plenty of space. So the match pair that I've been given, I usually use that if I can. You could choose to use this, that's fine. I'm going to go ahead and use angle A and side A. So A over sine A is 20 over sine of 65 degrees. This is equal to side C over sine of 72.2 degrees. And now to find side C, we just have to multiply both sides by sine of 72.2. .01 or 21.0 if I use the same number of significant digits. Which is bigger than 20, so that jives. Questions on that example? Okay. Okay. Let's do another one. Now here's an example where we have two angles and one side. If you have two angles and one side, you can always solve this using law of sines. First of all, if you know two angles, you could just find the third angle. And regardless of which side that you were given, since you basically know all three angles, you have a matched pair of an angle and a side opposite that angle. So, so we'll start by finding angle A. Let's get 47 degrees for angle A. Notice there's no risk. You know, I don't have to use arc sine to find an angle right now, so like those are good. We just use law of sines to find side B and side A. So let's find side A. How do I start?
Sine, right, well, 59 over sine of 25 equals
Oh yeah. So let me do this first. But then you're right. So A over sine A is 59 over sine of 25. And then, oh, sorry, that's C over sine C. Yeah, okay, good. And then what's on the other side of this?
A over sine of 25.
Mm-hmm. If we're using law of sines to solve for a side, it's really just a simple multiplication that we need to do now. So A is 59 times sine of 47 degrees divided by sine of 25 degrees. And we get 102.1. It makes sense that, oh, not degrees, jeez. Ah. I need more coffee. It makes sense that this is longer than side C, right? And when we find side B, we're going to expect that to be longer still. So. Okay, let's find side B. How do we start that? Yeah, we're going to do it the same way, right? So I can use the same, C and angle C. So C over sine C equal to B over sine B. So that gives us 59 over sine 25 equals B over sine of 108. Now we just multiply both sides by sine of 108 degrees. Wait, 25. Hold on. 132.8. Feet. Which is the longest side, so that jives with what we would expect. Questions on that example? Okay. So I want to return, just talk for a few seconds about this first example we did, because we were finding, we had to use arcsine to find an angle, and we know that arcsine as a function is limited, right? It's only going to spit out an acute angle. It didn't bother us here because we knew that this side had to be, or this angle had to be less than that angle. So we knew to expect an acute angle. There is sometimes ambiguity in the information that's given. So if we are given two sides and the angle opposite one of those sides. Sometimes there's two triangles that might satisfy the given information. So I'm going to start and just say, if I know, what's the given information? If I know two sides and the angle opposite one of those sides. So let's say, here's my known angle, and here's my two sides, right? I know A, I know B. Depending on the information that's given, it is possible that there could be two triangles. It's possible there could be one triangle. It's possible there could be no triangles. And it really has everything to do with thinking about this right triangle first. So again, the given information is angle A, side B, and side A. So I imagine first, if this were a right triangle, I would know exactly how to find, A should end up working out to what SOHCAHTOA would tell me, right? And when you use SOHCAHTOA to find like what the height of that right triangle would be, that's the minimum length that you need to have, and even to get a triangle. If A is shorter than that length and the height of that right triangle, then you have this sort of scenario here. A just isn't long enough to connect to that bottom side. So I imagine when I have an angle that's fixed, so this is like welded at that angle right there, right? But this is a hinge up here. So this side can just swing wherever. This side is fixed and this length is fixed. If A is too short, it's going to just hang there. It's not long enough. So H, if I find like the height of that right triangle that would have this angle A and hypotenuse B, that's a minimum. So A has to be at least that long. If A is less than that height, there's no triangle that you can draw. If A is longer than B, then there is but one triangle you can draw. I'm going to go all the way down to the bottom here. If A is longer than B, the only way, so this side's fixed and this angle is welded shut. If A is longer than B, then the only option is to have it extend out this way, right? But there's a sweet spot. There's a sweet spot that allows you to draw two triangles. And that is right here. So A is longer than that height, H, right? So it'll not only hit that bottom line, but it would go even below it if it were extended straight down. So I have to swing it out one way or the other. But so if it's longer than H, but it's shorter than B, I have a choice. I could swing it out in this direction, or I could swing it back in this direction. And the two triangles I get are this big triangle or this sort of this nested littler triangle here. And compare angle B and B prime, where you get different angles. Arc sine, when you use law of sines to solve this triangle, arc sine will only give you this angle, that acute angle. But it won't give you this one, because that's obtuse. So if it's the ambiguous case, and again we start this by saying I've given one angle and only one angle, and they've given me two sides and one is the side opposite, right? So I have to start just by saying, finding that value H, can I draw a triangle at all? And is that side bigger than, or is it between H and B? If it's bigger than B, there's one triangle, perfect. There's only one triangle we can draw. But if it's between H and B, I have to then consider them. So this is like a trickier case, right? We have to be a little vigilant about paying attention to the information they've given us. We're going to do some examples. So they didn't draw us a triangle here, because part of our task is to figure out, do we have a triangle at all? And if so, do we have one or two that would fit this information? Usually the first thing I do is I kind of sketch it out. And obviously I can't sketch the full triangle right now, but I can start with the information they gave us. I always start by putting whatever my known angle is over here, like on the left. I'm a creature of habit, so whether that known angle is A or B or C, I just put it over here. This angle is going to be fixed at 26 degrees. So there's side A. And then the other fixed side, I draw like this side going angling up. So I'm going to put side B at 41 centimeters right here. That means that angle C is up here. Angle B is going to be somewhere over here, you know, or if it exists at all, right? But I'm kind of stuck. I'll note that side A is less than side B, so there's either going to be two triangles I can draw or no triangle I can draw. So I've got an incomplete picture right now. I'm just going to do that. What I have to do first, since side A is less than side B, the first thing I want to do is figure out what is this height. And again, it's a perpendicular height. This is 26 degrees. So we can use SOHCAHTOA to find that height. We know that sine of 26 degrees is h over 41, just looking at this right triangle. So that means h is 41 times sine of 26 degrees. $17.8. So what does that what does that tell us? Can we draw a triangle? Yeah, the opposite side, side A, is at least as big as H. So that means it is in fact long enough to extend down to that bottom side. And it's bigger than H but less than B. So in fact there's going to be two triangles that we can draw. So I'm going to start, let me kind of make this a little bit more full, a little bit more complete. Something like that. One of the triangles will have B as an acute angle, and the other one, which I'm just going to draw as a dotted line over here, that'll be B prime. The other triangle has angle B prime is an obtuse angle. We always start, when you're in this situation, when it is the ambiguous case, when you do have two triangles you can draw, we find the first triangle that we're going to solve for is the one that arcsine will give us, where angle B is acute. So first, let me just write out our conclusion. A is between H and B, and that means that there are two triangles. So the first triangle, acute angle B. Oh, we know side A. Let me label that 25 centimeters. So we can use law of sines. We have the matched pair, right? 25 over sine of 26 is 41 over sine of B. Cross product here gives us sine 25 times sine B is equal to 41 times sine 46 degrees. And then we divide by 25, so sine B is 41 times sine 46 degrees over 25. Oh, 26. Thank you. Good looking out, everybody. So B is arc sine of 41 sine of 26 degrees over 25. Or is 46.0 degrees. So I have angle A, we have angle B. What can we find next? Angle C. Once we have angle C, then we can find side C. One oh eight. Now let's find side C. So C over sine of 108 is equal to, and I'll use the match pair they gave us, 25 over sine of 26. That means that C, if we just multiply both sides by sine of 108 degrees, we get 25 sine of 108 over sine of 26. Fifty-four point two centimeters. And that is the longest side. It's longer than the other side, so that jives with angle C being the biggest angle. In the ambiguous case, you know, we went through all the trouble of making the observation that there were two triangles to solve. So just be careful and make sure that you solve it, the second triangle. Like, we just did a bunch of work and we solved the triangle and it could just feel like we're done. But we have another one to solve. With the other one, though, this is going to be less work than the first one, I think. Not no work, but when you have the ambiguous case, right, you use left signs and you get this triangle with that acute angle B. This obtuse angle B is like, if you look at this right triangle and this right triangle, this little nested right triangle with B, C, and then whatever this point we want to call, right? And this triangle, B prime C, and that point, these are the same triangle, right? It's just one flipped around, you know, they're mirror images. So this angle here, this acute angle, which is not a part of any triangle that we're trying to find, I'm just sort of explaining how we get angle B. The measure of this acute angle right here, that acute angle has to be the same as that. And so when you're finding that other triangle, this angle that we want, this obtuse one, is just the supplement to angle B that we found. Just going to subtract angle B, 46 degrees, from 180. And that'll give me that angle. So the second case, I'm going to go down here, I'm going to draw it fresh. So the obtuse angle is always going to be 180 minus the given angle, or not the given angle, the angle that we found. which is 134. And now if we draw this, so this is 41, this is 25, this is 26. We know that this is 134 degrees. So we need to find angle C, and I guess I should call that C prime, and side C. So if angle B is 134 degrees, then angle C, I know the two angles, well, you know, they have to add up to 180, so 180 minus 134 minus 26. That's 20 degrees. C prime. And now, like before, we can use law of sines to find side C. So, or C prime, I guess. I don't want to use the same letter exactly for two different quantities in the same problem. So C prime over sine of C prime is equal to 25 over sine of 26 degrees. Ah, yep, thank you. A lot of the so that would be an unfortunate error. If I did that and found C prime, I'd stop here and I'd scratch my head for a while because I'd probably find that little side C prime was too big, right? So C prime is 25 times sine of 20 degrees divided by sine of 26 degrees. $19.5. Which is shorter than the other sides, and that's what we would expect because that's the smallest angle. Oh man, we are gonna finish this section, you guys. Are you excited? Liz is excited. I can tell. No. No, we're like 2 yards from the whatever you call it, the end zone. Is the time for football analogies over?
You had all of Sunday to review.
Yeah, I didn't watch. This is the first. I didn't watch the Super Bowl on Sunday. I usually do, but I just don't care enough about Kansas City or San Francisco as teams. You know. Well, yeah, I knew that. Okay, let's do one more. Again, we'll note that they've given us an angle and a side. They've given us one angle and a side opposite one of those angles. Are we excited? Okay, I'm going to start by drawing the angle on this side. Some people like to draw it on the other side. Like, I'm a creature of habit. I'm always going to draw it here. It's just how I think about it. So there's my fixed angle, 62 degrees. Side B is this side adjacent to the angle, 855. It's not how we have to draw it, but it's the way my brain works in these problems. And then side A is 415. So the first thing we have to do is figure out, can we make a triangle? So let's find the height. How do I find that height? Oh, yes, 62 for A. Let me fill that in. 62 degrees. So how do we get the height?
So it could be 415 over sine of 62.
That's not how I find the height, like, that's in red, right? That's a right angle there, right, if I'm finding the height. So this is like the only scenario just about in this chapter
So we could
where you can use right triangle stuff. Like, we made a right triangle.
Just subtract 180 minus 90 minus 62.
I could if I want to find that angle, but what I want is this height.
do cosine of 62 equals h over 55.
Why cosine?
Because we have the hypotenuse of the right triangle.
And what other side do we have of the right triangle?
But we're looking for h. Oh, wait. That's fine.
Which function do we want to use? Say that again?
Sine.
Yeah. So sine sine of 62 degrees is the height divided by 855. And so that means the height is 855 sine of 62 degrees. Let's find that height. We get 754.92 meters. What does that tell us? It's larger than side A, so this H is longer than this side. What does that mean? It's not gonna, if this were a hinge and just hanging there, this just hangs, it never touches. It's not long enough to make a triangle. So side A is less than H, and that means that there is no solution. You thought this was going to be a long one again. I put the triangle, this problem on its whole page all by itself. Filled you with a sense of dread, and then it got better. You always end a class on a high note, and then we're leaving feeling like, oh, that wasn't so bad.
Realistically,
Right?
855 and 415, 62 degrees is a
What?
small angle.
What? Let's do more? Liz wants to do more.
Liz can stay out.
Okay, Liz can stay. All right. So that's it. So that's law of signs. On Thursday's quiz, it'll cover vectors and law of signs. I will have a practice quiz in 212 in a bit, and it'll be posted to Canvas. So come by to work on it, or if you can't come to recitation, just make sure that you spend some time on it. I'll have the practice quiz posted, and hopefully I'll get my solutions posted tonight or by the morning. I just haven't written them out yet. I have to find the time to do that. So, all right, thanks everybody.